In this video, we are going to see the color models. So, before going to color models, I would like to see the motivation behind the use of color in image processing. There are two main principles that motivate us to do and color image processing. The first one it is that to identify an object and to extract that particular object from the scene. And the second one is, as humans, we can discern thousands of color shades and intensities compared to some dozens of gray. So if your matter it is in gray and image, it will be having some limited quantities of shades, but if you go for color images, it will have more shades, we can recognize more. And this is the two main principles or factors that why we are moving for in color image processing. And based on color image processing, we are having so much of models available. So what the main parameters color image processing have? The first one it is brightness, second one hue and saturation. Brightness, it is the amount of intensity of light that falls on a particular object, it is brightness. And hue is defined as the color that is perceived by an observer, it is hue. How much color or how much the light intensity the observer perceived, that is hue. Saturation is the amount of the white light mixed with the hue, that is the original color. How much white light we are blending with the original color is the saturation. So color fundamentals, we have gone through this in our lower classes in physics labs. That is when we pass a white light through an optical prism, we will get the Vibgyak color. So in the same way, your raindrops act as a prism and it produces the rainbow. This is the basic principle behind the rainbow. When the sunlight falls into the raindrops, the raindrops acts as a prism and make that sunlight as to view as in Vibgyak colors. So the Newton discovered that beam of light passes through the glass prism when that particular white color sunlight will split into a spectrum of colors. Okay, when Isaac discovered that he was just 24. This is the range of wavelengths comprising in visible range of electromagnetic spectrum. So our spectrum, visible spectrum, lies between 400 to 700 nanometers. In color fundamentals, we have seen variety of colors. The basic primary colors of light is red, green and blue. Okay, and the mixing of these particular colors will produce several colors. The main proposition or the main secondary colors are the magenta, cyan and yellow. So magenta can be prepared by combining red and blue, cyan with can be by green and blue, yellow can be by red and green. So mixing of these primary colors and also with the secondary colors, we get different amount of colors. When we mix these primary colors, it produces the white color. When it is come as an pigmentation, that we are defining some parameters, that is pigmentation. In the sense, the primary pigments are magenta, yellow and cyan, and the secondary colors of pigments will be red, black, red, blue and green. So when we combine these secondary colors or primary colors of pigments, that is magenta, yellow and cyan, we can produce the black color in a proportion while combining with red, green and blue in an equal quantity. It produces the white color. So there are three basic quantities that describe the chromaticity of light. The one it is radiance, luminance and the brightness. Radiance. Radiance is the total amount of energy that falls from a light source, that is measured in watts. And luminance, it is the measure of an light or intensity that is perceived from the light source by a human. It is luminance, it is measured, that the unit is lumens. Brightness, it is the how much amount of particular intensity of light present in that object, it is the brightness. And color models. A color model can be called as a color space or color system, and it is having a 3D coordinate system. So most of the color models we are using here are oriented towards the hardware, such as color monitors, printers, or some other applications like color graphics, creation for animation. And in apart that, we are having four different color models: RGB, CMY, YIQ, and HSI color models. So each color model defines on its own specific applications. The first color model is RGB color model. It is used in the color monitor or the video cameras, and the value of all the RGB's normalized value will lie between 0 to 1. When a digital representation, each color is represented by a fixed length of bits. Supposing we define with 8-bit image, so we are having RGB color. So 8 into 3, you will be having 24-bit RGB color. RGB image. So in real time, it is called as 24-bit RGB image. Actually, each color of that pixel will be represented in 8 bits. So this is that particular number of bits that is used to represent the particular image is called as color depth or pixel depth. So this is the geometry of an RGB image. So it look like a cube, or RGB cube. So in the center grayscale, that varies from white to black. Black represents 0, 0, 0, and white represents white 1, 1. So on G axis, a green axis will be available. On red axis, a red color will be available. So 1, 0, 0, and the blue axis, only blue color available. So 0, 0, in the value of blue, it is 1. So in the proper compositions of the red, green, and blue, you can obtain the magenta, cyan, and yellow that are represented in the other edges of the cube. So next, it is the color value representation. So when what to say, it is we couldn't say all the colors are faithfully retrieved. So we are saying some subset of colors. So that are the colors that when different hardware components are used for a variety of systems, we can reproduce it faithfully. In that particular category, the color falls as it is safe colors, safe RGB colors, or sometimes it is called as all system safe colors. So in internet applications, it is called as safe web colors or safe browser colors. On the assumption of 256 colors, the minimum number of colors that can be faithfully reproduced by a system will be 216. These 216 colors are called as the safe RGB colors. The number representation. So each of the 216 safe colors formed, the value can be represented as 0, 51, and 102, 153, 204, and 255. This RGB triplets, that is give us we are having 6 values, right? 0, 51, 102, 153, 204, and 255, 6 values. So we are having 3 RGB components. So it is 6 power 3, it is 216. So I said earlier that it is we can reproduce 216 colors out of 256 colors, right? So this there comes the value of 216. So 6 power 3 it is 216. So faithful combinations of colors will be 216. This is the hexadecimal equivalent of that number 0, 51, 102, 103. So this is the second one is the RGB system. So in that the first box represents the white. So the white, it has the square in the top array, it has the value of white. So white, it is the purest color and it is the greatest one. In case we are having black and white image, we represent 0 as black and 1 as white. So white is the greatest value. So here also white is the greatest value. So the greatest number in hexadecimal, it is the F. So we are representing as F, 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 F. 6 F's. So why it is 6 F? It is for 2F for R, 2F for red, 2F for green, and 2F for blue. Okay. So and the second square value will have, it is double F, and C. Third F will have double F, and 9, and so on. It will be moving. Next part is CMY model. CMY model is the cyan, magenta, and yellow model, which is a subtractive model, which is respect to the approximation of the colors. So we can represent the CMY model as 1 minus RGB model will get the CMY model. And another one, it is the HSA model. So HSA model, even though we are having RGB model and CMY model, it is not good for human perception. Sometimes we are seeing at the sky, the brighter colors will falls on our eye, so we couldn't recognize what is that object is. So we are moving for HSA model. So HSA model, where H represents the hue, saturation, and intensity. So I have defined it as an in previous slides. So we directly move. So this is the HSA model. So it is a conversion between RGB to HSA model. It is really complicated, so I have given some formulas, and the intensity is given by R plus G plus B. So this is the relationship between the RGB model and the HSI model. So the center plane we are taking is the plane of our interest. So by rotating the shader plane above the vertical axis, we can obtain different hues, and also if we move the geometrical representations by defining that formulas, we will see it is in the later slides. Okay. And this is the center plane, that is a red to blue plane. So when we move the center plane on the black and white axis, we will obtain different gray level values. The second graph, it is the second one, it is the hue saturation in the HSI model. The dot okay, yeah, there is the hue saturation on the color model. The dot that represents the arbitrary color. So and the angle from the red axis gives the hue, and the length of the vector as the saturation, and the intensity of all colors in any of the planes is given by the position of the plane on the intensity axis. So we can define like this. This is the intensity position given on vertical axis when we are taking the plane as an circular model, and the formula conversion for RGB to gray. So theta is the value we are giving, and if you want hue and H component in an RGB image, H is equal to some Q when blue is less than green, and 360 minus Q when blue is greater than green. And if you want the theta component, that is the cos inverse of 1 by 2 into red minus green plus red minus blue divided by red minus green the whole square plus red minus blue into green minus blue the whole power 1 by 2. And saturation component, we are having 1 minus 3 divided by r plus g plus b, and intensity 1 divided by 3 into r plus g plus b. And HSI2 RGB model. So here the application depends upon the values of the H. So we are having three main sectors from 0 to 120, 120 to 30, 120 to 240, and 240 to 36. So on the different values, actually the H returns a value of 0 to 360 degree. So you are having three sectors. So with this we can find the red, green and blue values.